Hi, I'm Peyton Degg, and welcome to Project Str-Eng. I didn't know anything about engineering or physics, and I'm on a mission to learn from industry professionals about what it takes to build the structures around us, whether it be our apartment buildings or the bridges we cross on the way to work. Join me as I try to understand how engineering affects our day-to-day lives, how structures are made, and what makes iconic structures so special. Tension and compression are fundamental ideas in structural engineering, and I can't wait to learn more about it. Let's dive in. History. The history of tension is closely tied to the development of engineering and the study of materials. One of the first uses of compression in building structures was the construction of the pyramids in Egypt. The stones were stacked on top of each other, pushing the materials towards each other and holding the structure upright through its compression. As new materials and new ideas were introduced into the world of structure building and engineering, tension became a key part of structural integrity, as structures became more complicated than just stacking bricks or stones on top of each other. For example, masonry and stone arched bridges utilize the compressive strength of the materials to support the weight of the bridge deck. Did you know that the world's largest game of tug-of-war had 6,282 participants? Even when thousands of people are pulling upon it, the rope stays intact because it's braided. This helps distribute the tension evenly, and the average rope can handle up to 5,500 newtons without breaking. Anyways, the Industrial Revolution marked a turning point in material science and engineering. Innovations in manufacturing and the use of new materials, like iron and steel, allowed engineers to design and build structures capable of withstanding greater tensile forces. The Industrial Revolution saw an emergence of suspension bridges, a remarkable advancement in tension engineering. These bridges use strong iron chains or steel cables under tension to support the bridge deck. This is the spot where cars and people are on, allowing for long spans over deep valleys and waterways. As bridges were constructed with various materials, engineers in the era of the Industrial Revolution considered the effects of compression forces on the structural components. The Industrial Revolution was not just about workers' rights and the urbanization of places around the world, but also about the cool and smart engineers that brought forward the ideas of tension and compression to structures we see on a daily basis. The interview. In the garbage, I can take your wrapper. Oh no, a chunk fell off. What is tension and compression?
Well, the basic form of tension and compression is when basically two forces are acting on an object. For tension, the two forces are typically acting away from one another. For compression, the two forces are typically acting towards one another.
So how does tension and compression affect our everyday lives?
Well, I mean, tension and compression is pretty much everywhere. For instance, the jungle gym that we're standing on, all of these vertical posts are in compression, holding everything up on the ground. This bridge, you would have tension at each connection, holding it together, preventing it from separating and falling. Same with the swing set over there. You've got tension in the chains that are holding it onto the upper.
And making it swing?
That'd be something different, but that's what stops it from falling off and allows you to swing.
So how is tension and compression used in structural engineering?
Every building, in order to stand up, needs various supports. Every office building, every house, every structure, in order for it to stand up, typically requires certain portions of that structure in compression to prevent it from just collapsing to the ground.
Why did you choose engineering?
From a very early age, I've always enjoyed building things, making things, creating things. Engineering gives me the knowledge of how to design those various components to make sure that they work and will last against, whatever's, thrown at them.
What's your favorite formula?
I'd probably have to say moment of inertia. It depends on the shape of something. There is no one formula per se, but depending on all the various shapes, each shape has its own formula.
Engineering was your first choice?
In grade 2, we had people come into into class and discuss, various types of jobs, and instead of picking policeman or firefighter or doctor, I basically came home and told my mom I was going to be an engineer.
Is there anything such as too much tension?
Yeah.
What happens when there's too much tension?
That's when things snap or fail. Yeah, I'm sure everybody's seen YouTube videos of people on swings who are way too large for the swing set, and as they're swinging, at a certain point, the chain or the strap snaps and they go flying, and that would be a failure in tension.
And is it the engineer's fault?
Well, depends. I don't think swing sets are necessarily like designed for like 280-pound people. I think at that point you've outgrown that toy. Yeah. But yeah, same with compression. You can have failures in compression. When they blow up buildings, you know, like demolition, what they typically do is they'll blow the certain columns which are holding a lot of compression. And then as each floor lands, that impact is creating too much compression that it wasn't originally designed for, which then creates that cascading collapse, because each level is basically collapsing under the weight of the level below, above it.
So when the World Trade Center was built.
Ooh.
What was your first job?
My last job before engineering was at Blockbuster.
Ooh.
Whoa, throwback.
Right at the very bitter end.
Yeah.
Yeah. You know when you go to engineering movies?
Yeah.
I don't know the name of it, but it was, oddly enough, Misha Barton from the OC.
Oh.
I only watched it just because in the description it mentioned she's a structural engineer.
Yeah. Have you seen the OC?
Oh yeah, of course. Who didn't watch that?
California, here we come.
I've never seen Friends.
That's sad.
Is it?
Do you think their apartment was designed well?
Yeah, engineering.
Well, I mean, aside from it missing, like, you know, two walls, and it's probably going to be a little cold at night. Yeah, there's a lot of conspiracy theories on, well, all kinds of like
Conspiracy theories.
all
Have you
kinds
seen the Seinfeld one?
Yeah.
Yeah, that one's weird.
Where like Kramer's, like the hallway doesn't exist type thing. Yeah.
Do you think that he wrote himself to be like this charming womanizer? Like, because he's always going on dates and he's always like, this woman wants me, this woman, blah, blah, blah. Do you think Jerry Seinfeld could really pull like that?
I would imagine he did once he became moderately famous.
Can you do a Jerry Seinfeld impression?
What's the deal? What's the deal with peanuts?
This lollipop was not very good. Was yours good?
Well, it's not bad. It's just. Yeah.
That's Andrew signing off.
All right, we'll see ya.
So basically, tension is a pulling force transmitted axially by the means of a string, rope, chain, or a similar object. Tension might also be described as the action and reaction pair of forces acting at each end of said elements. Compression is the application of balanced inward pushing forces to different points on a material or structure. The tensile and compressive strengths are key components to designing structures. That's the end of today's episode on tension and compression. A special thank you to Andrew for teaching me about tension and compression, and a special thank you to you for watching until the end of the video. I hope you learned as much as I did. Like and subscribe to see more of me and my engineering friends, who will teach us both about structural engineering. I'm Peyton Dagg, and that was another episode of Project Str-Eng. Don't forget to enjoy the process.
Could have been a nicer day.
I know, right? It's beautiful.
Yeah.
We were scared it was going to rain.